Okay, thank you, Prahladh. And I'm really sorry for not being able to be there in person. In order to fix that, I did have some South Indian food for dinner this evening. But yeah, the rest of it, I guess, would require it until next week. So thank you all for coming to this talk. I know Zoom talks are maybe not super optimal, but I'll try to do some justice to it. So I'm going to talk about some recent work on local codes. I'll tell you what those are very soon. And this work is somehow based on a new connection to certain class of spectral methods based on the so-called Kikuchi matrices. Now, we actually discovered these Kikuchi matrices in the context of some algorithmic problems. But today I will present a different view via a class of problem in combinatorics that also has basically a long history, almost as long as the study of local codes in computer science itself. And, I'll try to argue that this connection is meaningful and in particular exposes a barrier to proving better results than what are known currently. So let me begin. What I'm going to do at first is introduce this class of questions that people have been looking at in combinatorics for maybe more than 20 years now. And, so we'll start with that, and then I'll show you, or I guess I'll introduce you this idea of local codes, another class of questions that computer scientists have been thinking for maybe 30 years or more. And then, I'll show you how they are intimately connected. Now, even though this connection maybe is not so difficult, in fact, it's very easy. As far as I understand, this connection maybe wasn't explicitly observed before this new line of work. And so I'm kind of happy to tell you this connection. That's kind of the main message of the talk. Okay, so let me start with these questions in combinatorics. The basic idea is that these are what are called the girth problems. So in particular, they are like, questions about how many edges can you pack in a graph while avoiding a short cycle and various generalizations, okay? So let me start with like the most basic one. This was a question that Bolobash asked back in the 70s. This is actually in his graph theory book, and it was resolved. It was proven as a theorem by Alon, Huri, and Lineal in a very classic paper. It says the following simple fact: says that if you take a graph on n vertices and say its average degree is d, so it has nd over 2 edges equivalently speaking, then such a graph must have a cycle of length logarithmic in n. Okay, so in particular, notice that when d is 2, when average degree is 2, the graph can be simply a giant cycle. So the cycle can be of length as much as n. And what this result is saying is that as soon as you have a little bit more than n edges, there must in fact arise a cycle of length basically log n. Okay, and you can have sharp constants that maybe are not super meaningful to us, at least in this talk. Now it turns out, in fact, like this constant is itself a matter of great research, and we know it's like tight if you replace, or I guess the best example we know of is a graph that avoids cycle of length about 4/3 log n, and so there is some debate about what the right constant here might be, but again, as I said, not of great interest to us today. Let me so of course, my interest is in coding theory. So let me make like a simple linear algebraic connection, which is at the heart of this. Okay, let me like translate this simple statement into a linear algebraic result. So what I'm going to do is associate a graph with a collection of linear equations where the variables correspond to the vertices of the graph. Okay, so basically for each edge in the graph, I'll imagine an equation which is 2 sparse. So if the edge is ij, then think of an equation which is xi plus xj. I don't care so much about the right hand side, so you can imagine like it's an equation of the form xi plus xj is 0 or 1 modulo 2. Okay. Now, notice that, this is a 1-1 correspondence, because if I at least work with the field of 2 elements, then the only coefficients are 0 or 1. And, you can think of the edges of the graph as describing which coefficients are non-zero. Okay, so in that case, each edge gives me a 2 sparse linear equation. And the nice thing is that in this interpretation, you can also ascribe a nice linear algebraic meaning to a cycle in the graph G. So a cycle in G, notice, uses every vertex, 2 times. Every vertex that appears on the cycle is in fact invoked 2 times. So if you add, all the variables appearing in the edges in a cycle, you get 0 mod 2. So in particular, a cycle in G must correspond to a linearly dependent subset of equations. Okay. So this, is a simple linear algebraic connection, a cycle being, a linearly dependent subset. Okay. Now here is how we can translate the result of Alon, Huri, and Lineal in linear algebraic language. It says that, if you take any collection of 1.1 and 2 parts in their equation, so a little bit more than n, then you must in fact have a order log n size linearly dependent subset. Okay, the way to appreciate this statement is that if I give you n plus 1 equations, they must be linearly dependent, and in particular the dependency can be as much as n plus 1 in size, right? But this result is saying that in fact, if you give me a little bit more than n equations, then in fact there must be order log n dependency. Okay, so that's basically the message of this theorem. Okay, so now I want to tell you certain extensions of this theorem that have been studied in combinatorics for a long time now. So I'll start, and you can think of this as like certain colorful versions of this basic girth problem. So let me describe this problem to you. Towards that, let's make a definition. I'm now going to work with edge colored graph. So I'll have a graph, but every edge in addition would also have a color written on it. Okay, and I'm going to call a cycle in such an edge colored graph weakly rainbow if the cycle uses some color exactly once. Okay, so every edge has a color. So when you take a cycle, you're going to use various number of colors various many times. I'm saying it's weakly rainbow if it uses one color exactly once, and perhaps a better meaningfully defined term is strongly rainbow, where a cycle is strongly rainbow if it uses every color at most once. Okay, so like basically no color is repeated. Okay, that's basically the meaning of a rainbow and weakly rainbow cycle. Now of course, so the question I'm going to be interested in is like, how many edges do I need to have in a graph in order to ensure that every graph with that many edges has a weakly rainbow cycle or a strongly rainbow cycle. Okay, now notice that such a result must require some assumptions on the edge coloring. I could otherwise color every edge with the same color, and then of course no such rainbow weakly or strongly property would be satisfied by any cycle. So what this kind of a very important work of Kivash, Mumbai, Surakov and Verstraete showed is that it turns out you need a very weak condition on the kind of edge coloring to ensure that there is always a weakly rainbow cycle. Okay, so this weak condition is simply a local constraint. It says that the edges incident on any single vertex must all be distinctly colored. Okay, they can repeat however we want, but if I look at the edges incident on a single vertex, they must be distinctly colored. Okay, and then what they showed is that if you take a graph with average degree at least log n, and it is properly edge colored, then there must be a weakly rainbow cycle of length order log n. Okay, that's what they proved. This paper, by the way, is very important. It began like a whole line of work on weak and strong rainbow cycles and so on that continues to this day. Now their result in particular for weak rainbow cycle is actually tight, and the example is just hypercube where you color an edge that changes coordinate number I as I. Okay, and then you can check for yourself that this avoids a weakly rainbow cycle of length less than log n. Okay, so this theorem is basically tight. Now in the same paper they actually conjectured that at the same density, in fact there must be a strong rainbow cycle, not just a weak rainbow cycle. And like I said, there's been a lot of work on this, on this question for the last 20-ish years, including various intermediate progress. But let me just mention the result from about last year, or like maybe a year and a half ago now, that made some monumental progress on this problem. Essentially, they resolved the problem up to some additional log n term requirement in the density of the graph. Okay, so this is the result due to Alon, Biochik, Sauerman, Zakharov, and Zamir, and they showed that any properly edge-colored graph with average degree at least log n times log n must have a strongly rainbow cycle. Okay, so that's basically some summary of this line of work on strong rainbow cycles. Now like I told you, my interest is in hypergraph problems. So let's try to generalize this whole story to hypergraphs. Okay, so far you might be wondering, why am I talking about this? This is not a combinatorics workshop as far as I know, but I'll soon make the connection to coding theory. Okay, but so bear with me in the meantime. Okay, so now if I want to formulate a problem for hypergraphs, I should first tell you what the notion of a cycle in a hypergraph is. Okay, and the way I'm going to do it is, now there can be many ways to define a cycle in a hypergraph, but I'm going to choose the definition that makes this correspondence that I told you between graphs and cycles before to extend. My interest is in linear algebra, so I want to define cycle so that it has the nice linear algebraic meaning that we saw for graph cycles before. So just like before, I'm going to think of a k uniform hypergraph on n vertices, as in 1-1 correspondence with k-sparse linear equations and n variables mod 2. Okay. Now, I should mention that, even though I'm sticking with mod 2 things here, everything I say generalizes to any finite field. Okay. But I'll continue to work with like mod 2 just for the sake of simplicity today. Okay. So a k-uniform hypergraph is in 1-1 correspondence with a k-sparse linear system. Okay. And then, you can think of a definition of a cycle in H as simply any linearly dependent subset modulo 2. Okay, I'm now forcing the correspondence by using this as a definition. Okay, equivalently, you can see that, this is simply a collection of hyperedges in H such that every vertex appears in an even number of, the hyperedges in this set. Right? If this is true, then, you just look at the characteristic vector of CIs, sum them up, and you get a linearly dependent subset because they add up to 0 mod 2. So this, this simple combinatorial definition basically makes the linear algebraic correspondence hold. Now, these kind of things have actually been well studied, and they're often called even covers, but I'm going to continue to call them mod 2 cycles or hypergraph cycles in today's talk. Okay, so we're going to be interested in the question that Bolo Basha. So let's start by asking this basic Girth problem. In fact, let's ask a very special case of it. We saw that in the context of graphs, about n edges imply that there is a cycle of length log n. Let's ask, how many hyperedges do I need in order for my hypergraph to always have a cycle of length about log n? Okay. So this question was actually first studied by Naur and Verstraete, Asaf Naur and Jacques Verstraete, and they proved this result. They proved that, if I have any hypergraph, k-uniform hypergraph with at least n to the k over 2 hyperedges, then it must have a log n length mod 2 cycle. Okay. And, you can think of, or at least you can rationalize this bound as follows. You can think of n to the k over 2 as square root of the maximum possible number of k-uniform hyperedges possible on n vertices. And so if you plug in k equals 2, then that's square root of n square would have been n. So you can think of, at a very rough level, the Aron-Huri lineal bound as saying that if you have square root of the maximum possible number of edges, then there is a log n length cycle. Some kind of birthday paradox, if you will. And, this is just saying that the birthday kind of bound actually extends. Okay. That if I have square root of the number of all possible k uniform hyperedges, then there must be a log n length cycle in it. Okay. And some of these polylogarithmic bounds appearing in the result were improved later on by Feige, but let me not harp too much about that. Let's ask, a more nuanced question. What happens in between this giant regime left open before us, n and n to the k over 2? For example, let's say I wanted to understand what is the minimum number of hyperedges required so that every hypergraph with that many hyperedges, if it's k uniform, must have a L length cycle for some parameter L. And now, the interesting thing is that, I can ask question for, let's say, L equals root n. Okay, something large, but not quite n. Okay. So notice that, if L is n, I should mention this, because, because of the linear algebraic connection, any n plus 1 set equations must be linearly dependent. So, if I have at least n plus 1 hyperedges, then the girth is at most n. So that's like the left endpoint of this curve, and the right endpoint is basically this result of Naur and Verstraete that I told you before. So what happens for L equals root n? One thing you might conceivably guess is maybe there's a sharp transition. There was kind of a sharp transition from n to log n in the context of a graph. So you might wonder, well, maybe very soon after I increase the number of edges after n, maybe a root n length cycle arises, or maybe any small cycle arises, right? Or, you could conjecture that maybe, this regime of Naur Verstraete is in fact tight, that, for root n length cycles, I need to go maybe all the way to n to the k over 2. Actually, a precise conjecture to this effect was made by Feige, who actually claimed or conjectured that there must be a smooth interpolation between these two extreme regimes. In particular, he claimed that if I have that many hyperedges appearing before in your slide, let me explain that bound in a second, then such a hypergraph must have a cycle of length about L log n. Now, the one way to interpret this bound that you have appearing on the left hand side is if you plug in L equals 1, then it amounts to n to the k over 2, so that's like the right extreme. And if I plug in L equals n, then the bound becomes n, so it's the left extreme. So it's a single parameter parameterization of this line appearing at the bottom, And basically what Feige says is that if your point L indicated by this curve, then there must be a L log n length cycle. Okay, and the point somehow is that he's conjecturing an interesting regime where there is a root n length cycle and into the 1/4 length cycle, etc., etc. Unlike the graph case where there was a sharp transition from like n to log n. So, their motivation was some other problem that let me not go into for today's talk, not quite coding theory. It turns out that, those applications are also interesting, but, not maybe in our context today. And there was, some work in trying to prove at least the case of k equals 3 of this conjecture, and some weaker bounds were obtained in these papers of Alon Feige and then Feige Wagner. But it was largely open, and then a few years ago with Venkat and our student Peter Manohar, we actually proved this result. We had some extra polylog factors, and our proof was kind of a little bit clunky in various aspects, and this was kind of addressed in later follow-on works. And so now what we know is that Feige's conjecture is in fact true up to some additional sub-logarithmic factor in the size of h required for it to be true. And it turns out that this kind of a new technique also yields a new proof of this Alon-Huri lineal Moore bound that I told you about before. But I'm not going to tell you the proof of this result at all today. I'm simply going to say that, okay, we now know the basic AHL kind of result for hypergraphs. So we can now actually, build on it. We can ask, what about hypergraph rainbow problems? So, let's maybe make the natural definition here. I'll have now a hypergraph, and I'm going to color the hyperedges with various colors, and I'm going to define a cycle, a mod 2 cycle, as weakly rainbow if, just like in the case of graphs, it uses a color exactly once, and strongly rainbow if it uses every color at most once. Okay, so that's the natural analog of the definition we had for rainbow and weakly rainbow cycles in graphs. And now, we can ask the same question: what is the minimum size of a properly hyper-edge colored H that guarantees a weak/strong rainbow cycle? Okay. But before we dive into another combinatorial investigation, perhaps it is time to ask, why are we all doing this? Right? Like, what have rainbow problems ever done for us? Why should we care about them? So let me take a sharp detour into coding theory and explain this connection, and then, come back to hypergraph rainbow problems and give you some results about them. Okay. So, the connection is to this theory of local error correcting codes, and let me describe the very basics of it. So you all know error correcting codes. I'm going to think of binary codes that map k bits into some larger n number of bits via an encoding map E. And this encoding map has this idea, this property, that even if I delta corrupt, meaning I corrupt delta fraction of the symbols in the code word, then even then there is like a decoding algorithm that can somehow recover the message I was interested in uniquely and without any errors, right? That is basically the basic problem of coding theory. Today I'm going to care about codes that admit especially simple decoding algorithms. So of course, because I'm imposing restrictions on the decoding algorithm, this makes the challenge of, this makes like the task of constructing such codes harder, and that's basically what we're going to be interested in. So I'm going to call a decoding algorithm local if it has the following property. In addition to a corrupted code word y, just like in the standard error correcting codes, this algorithm will also take a bit I of the message as input. Okay, so think of it as like I'm interested in decoding the ith bit of the message. This decoding algorithm then can only do one thing. It can read at most q bits of y. Okay. So q will be very, very small. In fact, this entire talk is about q equals 2 or 3. Okay, so it reads 2 or 3 bits of this corrupted code word y. And then based on this, it is supposed to output, the value of bi, or guess the value of bi. Now notice that, any such algorithm must necessarily be randomized, because if it was deterministic and decided once and for all that it's going to query, let's say, first 2 bits, then you will corrupt exactly those bits and you will never actually succeed. Okay, so the output therefore is actually, should be correct with high probability over the randomness of the algorithm. The decoding problem is worst case. Y has no randomness in it. Okay, but the randomness here is over the random choices of the operation of the algorithm. Okay, and I'm going to only be interested in beating random guessing by some fixed constant advantage. Okay, that does make sense? Like, please feel free to ask me questions. If I'm saying anything confusing. Good. Okay, so that's the problem of local decoding. I'm just going to note the parameters that we encountered here. Delta was the amount of corruption I handle, epsilon was the advantage in guessing, and Q is the number of queries. In fact, for this talk, I'm going to think of delta and epsilon as just some fixed small constants. So we are only going to worry about one parameter, that is Q. Okay, good. So, let me also introduce a slightly stronger object, namely locally correctable codes. And in order to do that, let me observe that at least if the encoding map is systematic, then I can just assume without loss of generality that the first k bits of the code word are in fact just the message bits copied. This is without loss of generality for linear codes, and something equivalent actually is true even if the code is non-linear. So, just take it from me that, you can basically assume that the message bits are copied in the first k bits of the code word. The reason I'm saying it is because then you can think of local decoding as basically being able to correct any of the first k bits of the code word by reading q of the other bits of the code word. Okay, so local decoding is simply locally correcting any bit of the corrupted code word but any of the first k bits only. And so, if once I phrase it this way, you can ask, why can't I correct all the bits of the corrupted code word? And that gives you the definition of local correction algorithm, which is exactly the same, except now I'm going to be interested in correcting any bit of the code word instead of just the first k bits. Okay, so everything else remains the same. Now, these objects have lots of applications. They were in fact invented at, the dawn of algorithmic coding theory, roughly speaking, but I'm not going to tell you too much about that today. Hopefully you're interested in them already. In fact, the most basic question about them that we're going to be interested in today is, do they exist? Okay, are there good LDCs or LCCs? And let me point out that this is a slightly more subtle question than one might imagine at first blush if you haven't seen them before. To notice, roughly the first paper that in fact talked about coding theory, Shannon's work, also established the existence of good codes, right? Like just probabilistic method suffices. It turns out that because of this local decoding requirement, there is no natural probabilistic model that generates locally decodable codes or locally correctable codes, and so even proving existence of these codes is in fact challenging. In fact, that's really all we do. Even to prove existence require basically some algebraic constructions. So this talk is not at all about algorithms. They're simply about the question of existence of these combinatorial objects. Okay, good. So let me explain to you what we know and what these new results are and this connection to hypergraph rainbow problems now. So, for two query codes, it turns out there is a very natural code, things that we might learn in like a very first class on coding theory and maybe in the first or two classes in fact. There's this Hadamard code. It blows up a k-bit message to 2 to the k length code word. It turns out that it's a linear two query locally correctable code and in fact therefore also locally decodable. This was proven surprisingly so. In fact, if you haven't seen this before, there is no better code. Okay, so it kind of looks an extreme regime. I'm only allowed to read 2 bits, so there is a code surprisingly, but also it requires exponential blow up and you can't beat it. And these lower bounds were established, which are nearly sharp in this papers, leading from 2002 until 2004. Okay. Good. So for 3 query codes, there is a natural generalization of Hadamard codes. You can think of Hadamard code as like evaluation of linear functions, with the k message bits as coefficients. If you view this k message bits as like coefficients of a quadratic polynomial, you get the so-called Reed-Muller code. Many of you might already know them very well. And there is a very natural extension of the Hadamard local correction algorithm that gives you a local correction algorithm, this time with 3 queries. And because it's a locally correctable code, you also, of course, have a locally decodable code. And so for a while, it was basically open, whether there are better codes, locally correctable or locally decodable. And then there was this breakthrough works of Yakhanin and Efremenko that showed that there are actually codes that are much, much better than Reed-Muller code. So you can think of this, block length that appears here as 2 to the some function that is smaller than any polynomial in k. Okay, so a polynomial in k would have looked like 2 to the constant times log k, and the exponent is tinier than every such function. Okay, so it's a sub-exponential block length, if you will. And such a 3 LDC was shown to exist by Yakhanin and Efremenko. We didn't know if this code itself is actually a locally correctable code. We certainly did not know of it. We may not have expected it, but we certainly did not know of it. And this in fact was asked as an open question by Yakhanin, whether this code that they constructed, the so-called matching vector family, matching vector code, could in fact be a 3-query locally correctable code. On the other hand, our lower bounds starting with q equals 3 turn out to be super weak. We know a quadratic lower bound. We know that we can't have, a code with just linear blow up, for example. And this was also established in the same sequence of words that I told you about for q equals 2. But really, there's a huge gap between k square and the best known construction. For 3 LCCs, there is basically an exponential gap. For 3 LDCs, there is still a large gap, and so on. And there's a lot of work which introspects why we are failing in this task of proving lower bounds or constructions. And there are some works that made some equivalence or connections between some widely open conjectures in combinatorial design theory, the so-called Hamada's conjecture of 1970, which is basically widely open for most cases. And they showed that there's basically a deep connection between resolving this Hamada's conjecture and proving that Riedmuller is optimal. Good. So a few years ago, with Venkat, our student Peter Manohar, and Omar Al-Rabia, we actually managed to improve this quadratic lower bound a little bit. We proved that in fact there is a cubic lower bound for 3-query codes. It's still far from 2 to the root log k, but it is some improvement. And then we actually can give some simple combinatorial proof, at least for the linear case, and I'll try to tell you this idea at least today. In fact, recently, we were able to generalize this argument in the right way and get like an improvement for all q-query LDCs. So for even query LDC, for even q, such an improvement was known again in this previous works. For odd q, it wasn't. In this previous work that we did this improvement for q equals 3, but now we know in fact that the same improvement can in fact be gotten for all q. And this, in fact, was also done independently in a concurrent work of Oliver Janser and Peter Manohar. So, we have 2 different proofs of this result now. This bottom theorem is actually about 3-query locally correctable codes, and this, is something that we were able to do last year. We proved that, in fact, for 3-query locally correctable codes, surprisingly, you can prove a much stronger lower bound. You can prove an exponential lower bound as opposed to these polynomial lower bounds that were known before. We were able to prove that n is at least 2 to the k to the 1/8 for 3-query locally correctable codes. And again, both the results, the LDC lower bounds and LCC lower bound written here, they extend to any finite field, but let me just stick to binary for today. Okay, so this is the bound, for any field. We do lose something in the field size, so any finite field is fine, but if its size grows with k, then it gets weaker subsequently. In particular, this result shows that 3 LDCs and 3 LCCs can be very different. There is a sub-exponential length 3 LDC, but there cannot be one now that we know. In particular, it shows that this specific 3 LDC that people constructed could not possibly be 3-query locally correctable because there is simply no such code possible. And it kind of shows that at least Riedmuller codes, like the specific code that I told you about before that achieves 2 to the root k block length, at least qualitatively speaking, is not that far from optimal. Okay. In fact, subsequently, I won't tell you all this story in too much detail, but there has been quite a bit of improvement in 3-query locally correctable codes lower bounds. There was a refinement of our argument from 1/8 to 1/4 in the exponent, and then there was a different argument, very nice argument that works for binary linear codes by Venkat and Omar Al-Rabia. Some special cases for the designs were resolved. It turns out that design case, by the way, already implies a solution to a new case of Hamada's conjecture that I mentioned before. So yeah, at least for this case, it turned out that it's not so much of a barrier. We could just make progress on the conjecture itself. And there's even a non-linear version of a lower bound that we had last year. Good. So in the next 10 minutes or so, I'm going to elaborate on this connection between LDC lower bounds and these rainbow hypergraph problems, and then tell you the results about them. Okay. So let's start by relating this LDC lower bound question to a question about matchings. We're talking about hypergraphs, so I have to connect it to hypergraph somehow. So this theorem actually, it's an observation that goes back to this first work of Katz and Trevisan that began in some sense a proper study of locally decodable codes. They proved that if I look at any, at least let's say linear Q-query locally decodable code, and you can actually do versions of this argument even for non-linear, but let me just stick to linear. Then you can basically think of the decoder that exists for this code as something of a very specific format. In particular, you can assume that you can describe the decoder by giving k hypergraph matchings. These are matchings on the code word bits. So, there are matchings on n vertices. N is the length of the code word. And you can think of the decoder as doing the following. The decoder, basically is non-adaptive in the sense that, it doesn't somehow make a query and then decide the next query is based on the answer to the previous queries. To decode a given bit I of the message, it simply takes the corresponding hypergraph hi. Hi is a matching, which means that, it never repeats a vertex. So, it basically is a disjoint collection of triples for a 3-query locally correctable code, if you will. So for decoding the ith bit, this decoder simply takes a uniformly random triple in hi and then adds the corresponding 3 bits in the corrupted code word you have received. Okay, so it's a very simple decoding algorithm. If I have to decode ith bit or first bit, let's say, pick a random triple in h1, add the corresponding bits. Okay, and that's what your guess for the first bit would be then. Good. So, the proof of why you can, and it turns out that this is basically without loss of generality. Okay, you can assume with some loss in parameters of this delta and epsilon that I wrote you before, that any LDC has a decoder of this sort. Any linear LDC has a decoder of this sort. Okay. So I'm not going to describe this proof, but it follows from like very basic considerations. So let me not like go into the description of this proof, but that's basically the connection to this hypergraph. The hypergraph simply is basically this union of HIs, these matchings. Okay. So now let me make a connection between existence of LDCs and this so-called hypergraph rainbow problems. Okay. So I gave you a connection to hypergraphs through this Katz-Davis result. Now let me make a connection to this rainbow cycles. So I'm going to do it in 2 observations. Okay, they're both very simple. Let's look at the first observation. The observation says, suppose you take a subset of hyperedges, S1 from the first matching, S2 from the second matching, SK from the last matching. Okay, let's say X is a code word. So X is an encoding of some message B. Okay, then this observation says that if I take this code word X, X is the uncorrupted code word, by the way. Okay. So if I take this code word X and I add up the bits that appear in any hyperedge in SI, in any of the SIs, then I can say something about what this sum should look like. Let me argue what it should look like. If I add up the bits in any C which lies in, let's say, S1, then by the decoding guarantee, I know that the sum of these corresponding bits must be B1. Okay. So for every C in S1, the sum of the corresponding bits in X is B1. So, in the left hand side, you have size of S1 copies of B1 being added together. But because I'm adding modulo 2, the sum is simply a function of whether the size of S1 is odd or even. In particular, if S1 has even number of hyperedges, then the sum is 0. Otherwise, it is really B1. Okay. And now repeat this argument for like, S2, SK, so on. And you basically arrive at this conclusion that the sum of the bits of X in any C in any of the SIs, union of SIs, should in fact be the sum of BIs, the message bits, corresponding to those Is for which SI is odd, corresponding to those hypergraph matchings from which I selected odd number of hyperedges. Okay, this is simply just adding up the equations that appear in bullet point number 3 on the left hand side, if you will. Okay, this is simply a property by the existence of this decoder that we just discussed. Let me build on this observation and make this following claim. Suppose now you choose this SIs. Suppose I choose some subset of hyperedges from H1, H2 and so on, such that the union of SIs is in fact a mod 2 cycle in the hypergraph defined by union of HIs. What does a mod 2 cycle mean? It means that it covers every vertex of the hypergraph even number of times. Okay, that's what basically union of SI being mod 2 cycle means. Okay, then notice that the sum of, by observation 1, every SI since union of SI is a mod 2 cycle, every vertex appears in an even number of hyperedges in union of SI, which means that if I add up all the xj's such that j is in some C in union of SI, I must get 0. Right? That's just a definition of being a mod 2 cycle. every vertex is appearing an even number of times, then they must add up to 0. If you combine this with observation 1, you know that if union of SIs is a mod 2 cycle, then the sum must be 0. On the other hand, observation 1 says that it must also be the sum of those BIs for which SI is odd. Okay. Now notice that if there was a mod 2 cycle, S1, S2, Sk, such that some SI was odd sized. For some I, let's say first one, S1 happened to be of size which is odd. Then, you have a contradiction, because I can just choose the first message bit to be 1, right? The sum of XJs must be 0 in union of SI because it's a mod 2 cycle. On the other hand, by observation 1, it must also equal B1 because S1 is odd, and let's say all the others are even. So you have a contradiction, which means that in order to avoid a contradiction, it must in fact hold that in any mod 2 cycle, the size of every SI is even. Okay, does it make sense? We just basically did like some very basic reasoning, just that follows from the existence of a good decoder like above. Okay, good. All right, so here's a simple corollary that there is a QLDC corresponding to some decoding matchings H1, H2, HK if and only if every mod 2 cycle in the union of HIs, this hypergraph defined by taking the union of the matchings HIs, uses an even number of hyperedges from each HI. Right? This is just basically to avoid the contradiction from the previous slide. The point is that this is imposing a condition on the absence of mod 2 cycles that uses an odd number of hyperedges from some matching. Okay. The if part I kind of argued to you on the previous slide. The only if part is easy to prove. It's just like basically some Farkas lemma type argument that this is the only kind of contradiction that can exist. Basically saying that if I have a collection of matchings H1, H2, HK such that there is no mod 2 cycle that uses an odd number of hyperedges from any HI, then in fact you can get a code, and that code is very simple. Just like define the linear equations that correspond to the decoding constraints and take basically the solution set of them. Okay, so don't worry too much about the only if part. It's very simple. Good. So in order to use this corollary, let's make a simple definition. I'm going to define a super weak rainbow cycle in a hypergraph as simply a cycle, a mod 2 cycle that uses an odd number of hyperedges, from some HI. Okay, you can think of the matching that matching that contains a hyperedge as the color of it. So there is a natural coloring of hyperedges to 1, 2, and k, and then I'm just defining a super weak rainbow cycle as a mod 2 cycle that uses an odd number of hyperedges from some matching. It's super weak because I defined a weak rainbow cycle before, if you remember, and that posited that I should use exactly one hyperedge from some H1. So it's super weak because now I'm saying any odd number is allowed instead of 1. Okay, good. All right, so we have a corollary that there is a QLDC described by H1 through HK if and only if union of HI does not have a super weak mod 2 cycle. So basically we made a connection between existence of a Q query locally decodable code and some absence of a super weak rainbow cycle in a K colored Q uniform hypergraph. Okay, this is like the connection between the rainbow type problems in hypergraphs and LDC lower bounds. Good. So let me just state what we can prove about this. You can interpret these old results that proved lower bounds on locally decodable codes as follows. This is basically a reinterpretation of the results. They say that for every even Q, so for every possible even number Q, if I take any Q uniform hypergraph whose edges are properly colored by K colors, okay, and suppose K happens to be n to the 1 minus 2 over this particular bound, doesn't matter too much what it is, up to some log factors. Okay, then so remember that every color class also has omega and hyperedges here. I guess I forgot to mention here, but that's basically what I mean. That's what's implied by this average degree bound here. Okay, then such a hypergraph must have a super weak rainbow mod 2 cycle. The point is you can interpret this lower bounds against LDCs as simply a theorem that says that a dense enough properly hyperedge colored hypergraph must have a super weak rainbow cycle. Okay, and this implies a lower bound on Q query LDCs, in fact the same lower bound that appears in the average degree bound over there. Okay, notice that it's a theorem of a very similar kind to this graph rainbow bounds that we saw earlier, but now it's extended to hypergraphs. Now, actually in this work with David Munakorea, Tim C.A., Siddhant Mohanty, and Benny Surakov, we actually showed that in the same regime, you can in fact show the existence of a weak rainbow cycle, meaning some mod 2 cycle that uses exactly one edge out of some hypergraph from matching. Instead of an odd number, we can show in fact that odd number is 1. Okay, good. So, you can interpret, or at least, I'm going to state the results that I told you before for 3 query LDC lower bounds, this paper with, Omar Al-Rabia, Venkat, and our student Peter. And then, later on this combinatorial and slightly sharper argument with, these other people, also as like a rainbow hypergraph cycle bound. Namely that if I give you a 3 uniform hypergraph with average degree n to the 1/3 up to some polylog factors, and it is properly edge colored, meaning the hyperedges incident on any single vertex are all of distinct colors, then such a hypergraph must have a weak rainbow cycle. And in fact, in both these cases, you can show that the length of the cycle that we are finding, this weak rainbow cycle that we are finding, is in fact roughly related to the average degree. Okay, this is again similar to what happened in the graph case, and you can show that if you're interested in weak rainbow cycles of this length, about order k length, then this bound is in fact tight. Okay, and so again the corollary is that we get a 3 LDC lower bound, this cubic lower bound I showed before. And I'm not going to describe this theorem, but this new theorem that we proved with Arpon Basu, Tim C.A., and Andrew Lin, and this independent work of Oliver Janssen and Peter Manohar basically also implies a similar result for all odd Q. Okay, now we'll come back to this issue of this is tight later on, because of course as I'm going to argue, we should expect better LDC lower bounds, but this tightness of these two results shows that there is something important that's stopping, in the sense that there is a barrier to current techniques, and it relates to this issue of finding weak rainbow cycles as opposed to super weak rainbow cycles. And I'll come back to this issue again towards the end of the talk. Okay, in fact, I think it seems like I only have maybe 3.5 minutes or so. So let me actually, not tell you anything about the proof. So I'm unfortunately not going to tell you about the Kikuchi matrices, but instead, let me, spend the last few minutes on this issue of, weak versus super weak, because I think that really shows what the way forward is supposed to be. Okay, so let me skip just this part, and let's go here. So by the way, this technique that I did not tell you about has many applications, which I will also not tell you about. So that's that. Okay, so let's come back to the issue of what we know about LDC lower bounds. So I told you, for 2 query codes, the story is essentially complete. We have a code, and we can prove there is no better code. For 3 query codes, our story is far from complete. Even with this so-called improvement, we know only a cubic lower bound, which is very far from the best known constructions of 3 LDCs. And for q bigger than 3, again, this improvement in fact dwindles in quantitatively what it gives. It's an improvement over previous bound by some fixed polynomial for any constant q, but it's still very, very far from the constructions that we actually know. So that's basically the current status. And sorry, the slides are a bit dated. This is no longer ongoing work. This is finished work that I told you earlier. It's on archive. But the point is that there's a big gap between the best known constructions and the best known lower bounds. And if I had to guess, I would strongly guess that the lower bounds can be significantly improved. In fact, I would conjecture that there is no 3 query locally decodable codes with polynomial blow up. Right, like you should be able to prove super polynomial lower bound on the block length of a 3 LDC, in my opinion. Okay, let me discuss how might we prove them in the light of what I just told you. Okay, so we saw this bunch of combinatorial concepts. We saw this notion of a weak rainbow cycle in a hypergraph, right? Again, there is a typo. The first one should be weak, and the second one is super weak. The weak one, basically posited that I should use some hyperedge exactly once. The super weak posited that I should use, some hyperedge an odd number of times. Okay, and the best lower bounds, like I told you, they show the existence of such cycles. In fact, they show the existence of weak hypergraph rainbow cycles of length which are about as small as it possibly can be. about length. The length of the cycles is, basically the average degree of the hypergraph. Okay. So this K thing, that I wrote about in the previous theorems. The point is that so these theorems, in other words, are not just showing existence of weak or super weak rainbow cycles in dense enough hypergraphs, they are in fact showing existence of short mod 2 cycles. You cared only about existence of these cycles of whatever length, but they end up proving that there are short cycles is the point. And for the length bounds that we are proving, like I argued, or I guess I claimed to you, the bounds are in fact sharp. You can't hope to improve on them. And so, we need a new method that can detect longer than K length, weak or super weak rainbow cycles. And this is, I think, what is missing in the current techniques and is like a major barrier that would likely allow us, if you cross, would likely allow us to prove significantly better lower bounds. There is a natural approach to it, which I can't describe to you because I did not tell you the technique that we use to make these improvements. So let me skip that part and end with like a list of open questions. I'll just take 1 extra minute, Prahladh. Sorry about going over, but I'll just like discuss this open question, given that there are like lots of amazing people in the audience who might help us solve these questions. So this is a major open question, and I don't know anything about it. So I'll just like pose it anyway, but it doesn't do much, if I have no way to attack it. Let me just point out that proving super quadratic lower bound on 4 query locally decodable codes would be a major improvement. I say 4 because, the case of even turns out to be significantly easier to attack here than 3. So my suggestion, if you want to think about this question, would be to work on 4 LDCs. And then the kind of techniques I showed you before yield a quadratic lower bound. And the question I'm asking is, prove a little bit better than quadratic. Okay, this may seem like a ridiculous quantitative improvement, but I think now that we understand what's going on in these lower bounds, it will require a significantly new technical insight. That's why it's an interesting question. Let me give you also interesting questions that I believe are more approachable. Okay, so I'll pose 3 questions and then I'll end. First is like, we are close to but not quite done with settling the 3 query locally correctable codes lower bound. I told you that, for design locally correctable codes, we can basically prove that Reed-Muller codes are optimal. For general binary linear 3 query locally correctable codes, this very nice work of Umar and Venkat shows that n has to be at least 2 to the root k, but it is log k short, short in the exponent. And for higher field, in fact, like if you wanted to work just on F3, then the best bound is still 2 to the k to the 1/4. This Yankovitz's improvement on Peter and my paper. So there's some scope for improving and proving that low degree polynomials are the best you can do, which will be a really nice theorem to have. I think at least the case of 3 would be completely understood then. It turns out, so I talked about this question of weak rainbow problem in hypergraphs, but in fact we also defined strong rainbow bound, where there's a mod 2 cycle that uses every color at most once, and you might ask is there an application of that, and it turns out there are very nice applications. If you prove a strong, if you prove a strong rainbow theorem for 3 uniform hypergraphs at the same average degree that we currently know how to prove weak rainbow theorems, so you don't want to improve the numerical bounds, you just want to upgrade the type of cycle you found that people in the case of graphs have been able to do, then you actually get improved 4 query locally correctable codes lower bounds, and this is due to a connection due to Umar and Venkat. Okay, so there is actually a point to even proving strong rainbow bounds for hypergraphs, not just weak and super weak. And finally, let me say that all of what I told you, at least the best results, the most general results I told you, still only hold over fields that are constant size or grow very slowly. Okay. And this is real. It turns out that when the field size becomes large, the question of making LDCs becomes significantly more, interesting and difficult. And in fact, it has applications there too. So, even for the case of 2 query LDCs with large alphabet, we actually don't know the right lower bounds. So it is a very interesting question to see if some of these new techniques yield any insight on proving LDC lower bounds in the large alphabet regime, where we basically have no improvement over the first and only technique that we know how to prove lower bounds, which is due to Katz and Trevisan from more than 25 years ago. Okay, I'll stop here. Sorry for going a couple of minutes over. I hope it made some sense.
Have a question or two before we go to the next speaker.
Hi. Can you hear us?
Yes.
Yeah. So, do any of these techniques say anything when you allow the number of queries to grow as a function of n?
Yeah, very good question. They effectively say nothing because there are exponentials in Q hiding in all these lower bounds. Yeah, it's a very, very good question. Yeah, maybe like that could have been the fourth open question. Can you adapt these techniques to say something interesting when Q actually grows? Because as you are hinting at, there is actually a very interesting regime around log n and like less than that where you can do cool things in terms of constructions, while these lower bound techniques don't say anything. Great question, and yeah, I don't know.
Thanks.
Any other question? So Pravesh, just quick, this one. So where in your proof did the difference between LCC and LDC come in your sketch? There's already
Yeah, sorry, yeah, I did not. Yeah, sorry, go on.
No, so there's a place where you had to choose the right-hand side. You could set one to be 1 and the rest to be 0. Is that the place for the difference?
Yeah. So I did not tell you. Yeah, I did not tell you anything about the LCC part. But so like let me maybe say two sentences. So in LCCs, there is also an equivalent hypergraph construction, hypergraph problem that you can relate to it. But instead of a hypergraph for every message bit, now you have a hypergraph matching for all the n code word bits. So you have n matchings. Okay. So a priori, it seems like you're getting a denser hypergraph, right? Like our hypergraph. So all the spirit of all this result was that if you take a dense enough hypergraph which is properly edge colored, then you know there is a short cycle in it. And if there's a short cycle, then it precludes the existence of a good locally decodable code. So if you do this same idea for LCCs, then you get even denser hypergraph. So it seems like you're winning because you created like n matchings instead of k matchings. But the problem is that the colors are still the first k matchings, right? Because there's the message, the independent bits you can choose, the message bits are simply still k. Okay, nevertheless, it turns out that the remaining n minus k matchings can be used with some cleverness. And so the key difference in the proof is really in like this reduction, from hypergraph problem to this, rainbow problems. But that reduction requires more work in the context of LCCs, where you utilize the n minus k remaining matchings to effectively boost the density of this properly k edge colored hypergraph problem that we defined. I can't quite like describe more details, at this level of abstraction, but basically like the message is that the remaining n minus k matchings, even though they somehow don't come with independent colors in the same sense that we talked about in the context of LDCs, can nevertheless be used to boost the density.
Okay, thank you. Let's thank Pravesh. Thank you, Pravesh.